welcome to today's information security lecture, and with this we start into the second topic. So maybe I first explain a bit what topic we will talk about. This will be system security. We will have 4 lectures. These will be the 4 lectures in November about system security, and we will start with memory safety. Afterwards we will take a look at side channels and microarchitectural attacks, and then afterwards we will also look at sandboxing. Today we will mostly focus on memory safety, but you can already start and check out this Menti up there. You see the code, and you can just open the Menti there. And I see that Maria is writing in the chat that most people arrive 5 minutes late. I will confirm whether this is the case. So I will check how many viewers we have. Let's see. So currently there's 44. That's not that many. So yeah, let's see. Maybe we have more viewers later on. Yeah, this did not work as expected, but let me just resize this window a bit, then you should be able to see the chat again. Yeah, now you can see the chat again, and I can see the slides here, but you can already log into this Menti up here, and if you log in there you should be able to participate in the quiz that we have at the start, and we will also have some questions in the middle of the lecture. Reactions in Menti are not active, it seems. Oh, let me check. I hope they are active. Oh no, I can see them. I can definitely see them on my side, but I think there's a different problem, that the window is not refreshing. I think now the window is refreshing, so everything should be working now. And yeah, I can also see the slides here. I will, as I said, wait just a few more minutes until people arrive. 5 minutes, sure. So I'm just rearranging the windows here a bit. Now you are not able to see the chat anymore, but you should be able to see it again in a second. Let me check whether this works. No, it doesn't work. Unfortunate. Yeah, okay, so this works at least. Now you will be able to see the chat also in the stream. Okay, so let's go ahead with the quiz. I first start with a question on the preference, and the question here is, whether you would prefer to have the lecture going from 9:30 to 11:45, including a 15-minute break, whether you would instead prefer to get up later and run the lecture from 10 to 12 without a break, like today, right? Today is also not the time for a break. And then from 9:30 to 11:30, also without a break. But it looks like the majority is here for getting up early and having a break. Okay, then I have to come up with something, because Maria told me that during the breaks she showed like 15 minutes of advertisements. So I need to come up with advertisements that I can show during these 15 minutes. Okay. So we now waited more time. Let's check how many people are in the stream now. We now have 63 people in the stream. That's not that many. I think there are a lot more students actually registered for the class. So I think it should be more than 100 students. Maybe let's use this opportunity to already go into the Q&A a bit. Let's see. Q&A. We already have questions in the Q&A. And let me just show them here. Intel or AMD. I have processors from both companies. Okay, that was the only question in the Q&A. But if you have questions at any point, you can always ask them. We can see also here in the stream, we can see there's 48 people currently in Menti. Yeah, please. Q&A. Please just join the Menti. I hope people will join the stream. Otherwise, they have to watch the recording, which is of course less fun. So, and the next part that we do is we continue with the lecture with the slides. So let me just move to the slides, and I will get back to the Q&A during the lecture whenever there's a good point in time where we can do this. Okay, let's start with the first lecture, and today we will talk about memory safety. And I got here and Maria told me, yes, Daniel, you have to talk about system security because you're a professor at this institute and you know stuff about system security. And I was like, I have no idea who did that so far. And that was Michael Schwarz. So Michael Schwarz did that until now. And I went to Michael Schwarz and he was like, yeah, but I'm now in Germany. I can't give the lecture anymore. I was like, maybe it's remote. Can't you stream this from remote? And he was like, no, he has other stuff to do. So he couldn't give the lecture anymore. Now I'm here and I have to give the lecture. And yeah, let's hope that I get this done. So still, I want to thank Michael for helping me out with the slide deck. Anyway. If you have to talk about something that you have no clue about, the first thing that I would do is to find some definition, right? I have to talk about memory safety, and therefore we can just check Wikipedia, memory safety. Wikipedia says memory safety is a concern in software development that aims to avoid software bugs that cause security vulnerabilities. Okay, that's already a quite complex sentence. I thought that Wikipedia was for everyone to understand. But, no, maybe, yeah. Dealing with random access, memory access, okay. It's getting more and more complicated, such as buffer overflows and dangling pointers. I have heard a few words from this sentence already, and many of those words are completely new. So maybe we should take a different approach. There are more details, of course, to memory safety. For instance, if we go into the details, there are different types of memory safety errors that we want to look at, and we will build up our vocabulary more and more in this lecture. So the different types of memory access errors that we have, or memory safety errors that we have, are access errors first, buffer overflows, buffer overreads, right? You might know them from C and C++ programming classes, where you have a fixed size buffer and you want to read into this buffer, and then the buffer is not large enough for the user input that was provided. That would be a buffer overflow. Invalid pointer, I'm sure you all have dereferenced invalid pointers at some point. For instance, the infamous null pointer that you dereferenced somewhere because something might have been not initialized, or maybe the pointer is for a different reason invalid. Maybe you have a race condition, right? So maybe you might know these from from system level programming or operating systems. You might know the race conditions where you access a shared data structure in multiple threads, and you have one thread that modifies it, and then it's inconsistent for the others. Also related to race conditions is use after free, where you use a resource after you already released it. So for instance, you have a pointer, you use free on this pointer, but you use it after you called the free function. This is also where the name comes from, use after free. Other memory safety errors are more about uninitialized variables, and I already mentioned the invalid pointer. This is more about pointers that are not valid, but not necessarily the uninitialized variables, but they can in some cases overlap. For instance, null pointer access because you initialized it maybe you initialized it to 0, or maybe the uninitialized value is already 0. Uninitialized pointer accesses. Another type of memory safety error, and you can see that they go in different directions. This is about accesses, this is about uninitialized things. The next is about memory leaks. It's also a memory safety error. For instance, if you leak variables on the stack, if you pile on more and more memory on the stack, then you might get into a stack or overflow, or a heap overflow in a heap. You might free variables that have already been freed, or that were never allocated, so it would be an invalid free, and then maybe another allocated data structure is not being freed instead. Also unwanted aliasing, if you have multiple pointers to the same data structure and you don't actually want that, and you can introduce bugs through that as well. All of these are program bugs, and we can prevent these program bugs from occurring by writing memory safe code. And this is not so easy, so we will talk about this for the next 2 hours almost. There are 2 types of memory safety violations. The first category is spatial violation. There you access memory out of an object's bounds. For instance, a buffer overflow, out of bound reads, null pointer dereferences. These are accesses to memory locations that you did not allocate at any point in time. The buffer was never larger than that, or maybe it was, but then it's a different case maybe. But a buffer that has a certain size, you write beyond it, that's a spatial problem. It's about the space. The other category is a temporal violation. And in a temporal violation, you have different, microphone is on the right setting. For temporal violations, you have, for instance, use after free, where you, as I said, use the variable after you already released the memory for it. Double free, where you call free twice on the same pointer, or you use uninitialized memory. So the use of the variable is not wrong, the free is not wrong, the use of this memory is also not wrong, just the point in time is wrong, and because the point in time is wrong, this becomes a bug, and then you free this multiple times because it has already been freed. The free would have been fine at an earlier point in time, but at this point it's an incorrect double free. So let me continue. I will get to a point where we can have a first round of Q&A, and I already see the question marks here. If you have any questions, feel free to post them in the Q&A section at any point, and I will get to these questions. If you have a question, you can also post it in the YouTube chat, and I will also react to the questions in the YouTube chat. You can see it up here, and yeah. And you can always use the question marks or thumbs up, thumbs down to tell me whether something is wrong with my explanations, or I should provide better explanations or something. So what is the motivation for this? Why do we look at memory safety violations? There could be different motivations. We will talk about different actors that are interested in these types of vulnerabilities. So maybe as a motivation, there is this CVE database, the Common Vulnerability and Exposures Database. And you can see over time the number of memory corruption vulnerabilities, so memory safety errors that they found in software and hardware that they track is increasing drastically over the last few years. And this is going up and up. We are not seeing a downward trend. So what do we learn here? The number of bugs gets more and more, and these bugs can be exploited. And they can be exploited by different actors, and we will talk about these different actors in a second. And first, before we go into all the more ugly and maybe also, before we also talk about ethical aspects, we will talk about how industry relates to these vulnerabilities. So there's a question in the YouTube chat. Are we sure there aren't just more incidents being reported while the number of incidents stays more or less the same? Yes, this can also be an effect, but also the amount of software that we have today is certainly significantly more than let's say 10 years ago. So the number of software, the number of bugs that we will have in software will also correlate to the amount of software that we have written in total. So I would also expect that the number of bugs overall increases. But definitely also we are getting better at finding bugs, and therefore we will also just find more bugs. The CVEs, they usually track distinct vulnerabilities in concrete products. There's also the CWE, which tracks categories of bugs. So you would, for instance, find that use after free is a category in the CWE database. And also this database is increased with every new type of bug that is discovered, every new type of vulnerability. In companies, you will find that today they often split their security teams into a red team and a blue team. Two types, two views, two perspectives on memory safety, but also to security in general. This is not just memory safety, this is security in general. The red team and the blue team are interested in making things more secure, but they will take a different perspective. The red team will usually take the perspective of an attacker. The blue team will usually take the perspective of a defender. Attackers try to violate memory safety. Defenders try to ensure memory safety. And this is often seen as a cat and mouse game. This is often seen as a, here it says, security war game, where the one team comes up with better attacks and the other team comes up with better defenses against these attacks. So the red team tries to find security problems and mount attacks. The blue team on the other side will, now you can't read this, and I can't read this. The blue team on the other side tries to come up with good defenses that will prevent these red team people from exploiting things. So the red teams, the red team are not only criminals. No, in general, if you would look at the term red team, you would more frequently find this in when talking about companies. They do this work so they find vulnerabilities to then inform the blue team so that the blue team can then come up with proper defenses. So the blue team develops defenses based on the attacks that the red team discovers. The red team then again breaks them, and then we slowly go into a spiral where security gets better and better, but we always stay in this spiral where you have attack, defense, attack, defense, attack, defense. This doesn't stop, but the overall security improves. The ultimate goal is, of course, memory safe programs, but this is a goal that we probably will never fully reach, because you will always have some parts that remain not memory safe by design, maybe because they interact with the hardware and their guaranteeing memory safety is very difficult. Also there are a lot of research proposals how to make things more secure and how to make things more memory safe, but it's still unclear whether we will have real world fully memory safe programs at any point. And it's difficult. It's a difficult problem to make programs in general memory safe. Let's talk about the red team first, because the red team is about attacks, and this is what we start with, right? There would be no reason to have a blue team if your software doesn't have any problems. So if there are no attacks, what would you defend against? So let's start with the red team. The red team, okay, attacks. We have to think about a fundamental question here. What is an exploit? And there again, because I don't know what an exploit is, I checked different definitions for this. And the Oxford Dictionary says it's a software tool designed to take advantage of a flaw in a computer system. Okay, this is a debugger an exploit? I could use a debugger to figure out how a flaw works and then take advantage of the flaw. Okay, I don't know. Wikipedia, let's say what Wikipedia says. Cause unintended or unanticipated behavior to occur on computer software. Well, I just need to put one of my parents in front of a computer, and you will have unintended or unanticipated behavior. Well, maybe so. Today, many of the parents already know very well how to use computers, but if you put the right user in front of the computer, you will have unintended or unanticipated behavior. What does Kaspersky say? Kaspersky say if Achilles' heel was his vulnerability in the Iliad, then Paris' poison-tipped arrow was the exploit. Yeah, this is. I don't even know what they want to tell me here. This is quite fuzzy. I don't know. So maybe let's come up with a better definition. And most of the ideas that we present here on these slides are based on ideas that Halvar Flake, or with the real name, he's called Thomas Dulien, that he presented at TU Graz 2 years ago, and that he also presented in several other talks. So we need to think about what a normal program is. So programs, well, we have programs, and if we take a machine, then a program would be a description of how to solve a certain problem. For instance, finite state machines, we might know them from Introduction to Information to Computer Science, or from Fundamentals. Is it called Fundamentals of Computer Science? Yeah, one of these lectures. I'm sure you have seen finite state machines somewhere already. We don't build such machines, but we have general purpose hardware that emulates them. Programs are basically emulators for finite state machines. Right? If you have a finite state machine as this one, you have state transitions, open and close, and you can move between these states, transitions. There's a condition often associated with the transition, and yeah, this is how finite state machines work. You have the states, the transitions, and conditions. If you have an input, then the state might change from one to another, And yeah, the finite state machine solves the problem that we wanted to solve, similar to a program. So basically, the idea is to express programs as finite state machines. There are many different ways to implement finite state machines, and we will look at a simple example now. This is a simple password manager, and this password manager, let's start here. We read the PIN from the user. We check whether it is correct. If it is not correct, we print an error message and go back to the start. So we read the PIN again. If it was correct, then we show the password list. This is a very simple finite state machine for a password manager. And the security properties here are, well, it checks whether the password is correct and then shows me the password. And otherwise, it doesn't show me the password. So the security properties of this finite state machine are based on inputs and outputs, right? The output is only, the secure output is only shown if you provide the correct input. In this example, for this finite state machine, implementation would be secure with respect to this finite state machine if it's practically infeasible for an attacker to get the password list, the output, without the input. And we know how to write an emulator for such a finite state machine. We have the processor. We can write a program on top of the processor, so we can basically simulate finite state machines on our modern CPUs. They have a lot more features than we need for our finite state machine, for our specific finite state machine, because the CPU is a general purpose computer. For example, in our case, reading the PIN already requires multiple CPU states, but for our security finite state machine, we might not care about all of them. We can see that later. We have keyboard interrupts, we have the reading of the keys, storing them in memory, etc. Not every CPU state is represented in a finite state machine. This is also something that we have seen. The finite state machine was very simple, so these were all not represented in the finite state machine. So we want to talk about 3 different cases of CPU states. Right? In a finite state machine, there were only, so in the one that we have shown, there were 2 states. But in the CPU, there are 3 cases of CPU states, or you could call it 3 types of CPU states. The first type of state is a sane state, and that is a CPU state that corresponds to a finite state machine state. We have transitory states where the CPU transitions from one state to another, leading to a sane state. So from one state to a sane state, to another sane state. And then there's also a weird state, which is a case where the CPU state does not correspond to a finite state machine state. Let's take a look at how these weird states work. And I've prepared a simple example here, or actually Michael Schwarz prepared this example. And this is a very simple password manager that you can see here. We have a main function up here. We have a PIN. We check whether it's correct. So we read the PIN. Then if the PIN is this number here, let me check. If the PIN multiplied by this number is this number here, then we set correct to 1. And if correct is 1, then we show the password. Otherwise, break. And then we print wrong PIN. So in the beginning, this is not a state of our finite state machine, right? This is not in our finite state machine. So the CPU state is transitory, still transitory. Now we are in a sane state because we are in the read PIN state. And we have jumped from this function over to this function here, the read PIN function. And we stay in this state for some time. So we now read the PIN, we print the message to the user, and you can see these are all additional states that we have in our actual implementation that are not covered by the finite state machine that we defined for security. Then we use getS here. We maybe get some environment variable and print a buffer here. So if the environment variable debug, it's for debugging, if this is set to debug, then we print the buffer that we have seen here. Otherwise, we use a to I, any to integer, and use this on the buffer to return an integer, and this integer is then used as the pin here. Okay, then we go into the getS function, then we go here, still in the same state. Now we are in a transitory state again, because we will go back into this function here. And now we are in the next sane state. We now are in the state, is it correct? This is the next state in our finite state machine. Then we set it to correct. So we are still in this check whether it's correct. So there are multiple states again covering this part. And then we are in a transitory state again. And in the next step, we would show the passwords to the user. So we are in a sane state again, showing the passwords to the user. And this again is a lot of single steps. Okay. So we haven't seen weird states here. These were only sane or transitory states. The CPU emulates the finite state machine. So the question is, how can the CPU enter a weird state? This should never happen, right? But it can happen if you have a programming mistake, if you have a broken hardware. For instance, if you can flip bits in memory, if you have hardware bugs, CPU bugs that allow to inject the wrong data into program's execution. This would be a weird state. Then the program does not know that it is in a weird state because the CPU does not understand that. The CPU doesn't have any concept of the finite state machine that you envisioned. The CPU believes it's doing the right thing. It's just processing one operation after the other. So the program just continues executing in this weird state. And the transitions might still apply. So it can be possible to go from a weird state to another state. For instance, back to a sane state. But also you can go from one weird state into another weird state. So this would lead to the weird machine, a machine which is not the finite state machine, but a weird machine that the programmer did not envision, that the programmer did not intend. And this has many weird states and transitions from one weird state to another. We can program the weird machine. Of course, we can program a finite state machine. We can also program a weird machine, of course, similar to the original finite state machine. And we will see that in a second how that works. Writing program code is one way to implement a finite state machine, right? We program a device, we give it instructions, right? We generate instructions and then the CPU executes these instructions. Maybe a question for the chat. Is there any other way how we can program a device other than giving it generating instructions? Can we program a device without generating instructions? We have already done that. If you think back to the finite state machine, our abstract finite state machine that had input and output, and the transitions between the states in the finite state machine were programmed by providing different input. The input is actually already a way to make a processor operate differently. So you program the CPU with the input. So to program a device, we have to generate instructions. As this guy would say, wrong is not correct. So let's continue. So we have to get rid of the mindset that we require code for programming. We can also program without writing code. So the program applications accept input, and input is one means to program a machine. The code that we provided for this application, that we wrote for this application before, is just a way to interpret our commands and translate them into the next layer. You can see it, for instance, like C code, how C code is translated to assembly instructions. And maybe on top of the C code, you have an interpreter implemented that interprets a weird, or let's not say weird because this term is used for today for something else, but an obscure programming language, let's say something like maybe JavaScript. JavaScript or JavaScript would very often be just in time compiled today, but you would have other languages that could be interpreted, and there you would translate the operations that the user provides as a script into assembly operations that are executed on the CPU. And on the next level, you provide input to this application, and this is translated, if you think through it, into the instructions that are executed on the CPU. If you provide one input, it will execute a different instruction after the branch, for instance, than in the other case for a different input. So the CPU does different things depending on the input. The input programs the application. The application is now the finite state machine that we program. So before we wrote instructions for the CPU, there we programmed the CPU. This time the application becomes the computer. We program the application, and the application becomes our general purpose computer in the best case that does exactly what we want. This is fine if input can only lead from one sane state to another, then we still program this application, but we program this application in a sane way as intended by the programmer, by the developer of the application. But what if we have bugs in our software? Then this changes. So we will bring programs now into weird state. So if you have user input that you can use to bring a machine into a weird state, the application into a weird state, then the attacker controls your computer. Then you're owned. You might have read this somewhere already. An abstract definition of exploitation. So we bring the application into a weird state by providing specific user input. Then the attacker controls your computer. Let's talk about exploitation. So if we want to exploit a program, we want to bring it from a sane state, and it starts in a sane state. We want to bring it into a weird state. So we have to choose a sane state which allows us to get into a weird state. And this is usually searching for a bug. There will be a bug somewhere in a program, and this allows us to move from a sane state into a weird state. And the instantiation then is the next step for the exploitation, and there we transition from the sane state into the weird state. And finally, the programming, there we program the weird machine. We continue to provide inputs such that the weird machine will act as we want as an attacker. And the goal here is, of course, to break the security properties of the finite state machine that the developer envisioned. We want to enter a weird state. Can we find a bug in a program? Can we abuse the bug to enter a weird state? These are basically the questions that we need to answer if we're in the red team. The first hint about a bug already occurs when we compile the program that we've seen before. And this hint is warning. The getAs function is dangerous and should not be used. Okay, who has already seen that warning? Please give me thumbs up or post in the chat if you, or post a cat or something if you already have seen this warning. Yeah, so many people have already seen this warning. So better not use it. Let's check the man page of getAs. Okay, maybe we have further hints here. I have to go a bit closer because this is a very small font. So what does it say? Up here it says get a string from standard input, and it says in caps, in capital letters, deprecated. Okay, let's check. Okay, here also see caps, bugs below. Okay, what else? Here, deprecates get as, POSIX marks get as deprecated. Is it? No, obsolescent. Okay. C11 removes the specification from the C language. It's not in the C language anymore if you use C11. Since version 2.16, glibc header files don't expose the function anymore. So they really don't want you to use it. So this must be dangerous. There will be a bug here. So let's check. Where's the bug? So we've seen this code. Read pin. Buffer. Buffer 16. Enter pin. Get as buffer, and then we have get environment variable debug, and we print the buffer if the environment variable is set. So let's check. Get as buffer. What could go wrong here? The buffer only has space for 16 characters. This is of course a problem because getAs does not take that into account. And that means if we provide a lot of user input, right, getAs reads until EOF, end of file. If we provide a lot of user input, things can go wrong. Let's take a look at an example. I use this password manager here now. I enter the pin, says wrong pin, and then enter pin again. And now I enter a much longer pin. This one. Let's see what happens next. Any ideas? What would you expect? Please post it in the chat. A segfault, absolutely correct. Oh, now you can. Okay. Yeah, a segfault is absolutely correct. Yeah, you can see it here. So this does not work. This is great. We can crash the program. That's already an achievement. That's great. Perfect. But actually, crashing a program is not that great. Crashing a program, I mean, we want to enter a weird state. If we crash the program, it's definitely not a state in our finite state machine, but also the machine basically just stops. But maybe we can take a closer look and check whether we can transform this crash, this transition, because the process of crashing might also consist of multiple states. Let's see whether we can exploit this and move from one of the weird states that occur during this process of crashing the application to get control over the application. We are in a weird state due to a programming mistake, and the mistake was nothing more than using the getAs function. Why did we get into this weird state? Yeah, this is something that we need to think about. And what is this weird state? Third question, how can we program our weird machine to do something useful instead of crashing? And the first question, we already mentioned that getAs reads from the user until EOF. So everything that we read is stored into this array that we provided there. And the array has a defined size. If we read more data than the array is large, then we will overwrite something else that is adjacent in memory, and this will lead to a problem. Let's think about the memory layout here. You might know this from computer organization or from system level programming also. What is next to this variable? Which variable will be placed next to this buffer? The local variable, so it is on the stack, and that means that there will be other local variables adjacent. In this case, we don't have any. There were no local variables. So what else is on the stack? Yes, the return pointer. the return address where we will jump to next. What else is on the stack? Yes, let's take a look. We have the local variables here. We have the base pointer, the old stack base pointer for the stack frame, and the return address that we will jump back to. And we overwrite this. Saved return address, saved base pointer, local variables. Let's see how this works with our example. So we have the example here, we can see the buffer there, and now we will call this function. We enter this function, we place the instruction pointer and the base pointer on the stack, we place the buffer on the stack, then we read data, and now you can see that we just overwrite these. And these definitely don't look like healthy pointers. So this will go somewhere. It will use some stack pointer then, some random number as a stack pointer basically. Some random number that the user provided as an instruction pointer. Wait a second, it's not random, it's user provided. So that means that the user provided actually this number here where the return will continue. Okay, this is interesting. Maybe we will get back to that in a second. So we are somewhere at this address. So the CPU tries to execute code at this address, and there's probably nothing mapped. Then we get a page fault, and then the operating system decides that it will kill this application with a segmentation fault because there should not be anything mapped there. That's what the operating system decides. And the weird state is the CPU trying to execute code at an invalid address. This should never happen. How did we get here? Well, we bring the CPU into the weird state by entering too many characters, more than the programmer anticipated here. The programmer anticipated that we will enter at most 16 characters. Yeah, this is quite unfortunate. So what we control is the CPU, the next instruction pointer that the CPU executes in this weird state. So now what we want to do is we want to either stay in a weird but useful state or go to a useful sane state. For instance, if there's already a function that would provide us with secret information, that could be very useful to target and to just transition to this sane state, from this weird state back into the sane state. But we can also chain up many weird states and leak information with that. So let's try to get into a sane state. Show password list first. Let's try that. And there's a question in the chat. Can't we just jump to any code that is compiled on that program? So anything in standard or any lib that was compiled with it? Yes, you are absolutely correct. We could jump to any of this. And therefore we choose a function which is already compiled into the program, which is the show passwords function. So we can let the CPU execute code at an arbitrary location. The user that provides input chooses which code address is executed. This is really, really bad. This is about the worst thing that can happen to your program if the attacker has full control over your application and can control arbitrarily what is executed next. This is arbitrary code execution within this application, and that's all that your program has to offer. The show passwords function is already there. We can just check where it is with readelf, grab for the function name. There we have the address. Okay, you can see it here. And now we will provide a pin with some padding. We have to figure out what the padding is, and then these hex characters. The padding fills the buffer plus the saved base pointer, because we don't care about the base pointer, and then the address will also overwrite the saved instruction pointer, the address that we provide here. Let's try this. So we provide this input here, echo, and then these hex characters, pipe this into password manager, and what happens? Interesting. So we get enter pin, okay. And we get our list. Interesting, we get the list of passwords, so this part worked. And then we get a segmentation fault, because what will happen after the show passwords function? Maybe someone in the chat knows what happens next after this function was executed. we will jump back. Yes, we will return again to the next function call in the function call hierarchy. And that means there might not be a valid function pointer there. So we will probably still be in a weird state where things easily break. So we broke the security properties of the finite state machine. That means that we are, that we have won as a red teamer, as an attacker. So the setup was we started the program with a sane state read pin. We just started the program very normally without any manipulations. Then we instantiated our exploit with too many characters that led to a weird state. Then we were in this weird state and we programmed the weird state, the weird machine, using the input to move to the sane state show password list. And then we have successfully developed our first exploit. This is an exploit. Can we do more? Well, actually, I said if you have arbitrary code execution, there's nothing more that you want to have within one context. Because with arbitrary code execution, you can do all kinds of different things. You can not only leak any data, but you can also overwrite the data. So let's think about the weird states here. What if so far we have overwritten the saved instruction pointer, but we could also overwrite other things. We could overwrite other memory location. So what about doing more than just overwriting a single saved instruction pointer? Maybe we can build a more powerful weird machine language. So one question that we need to ask here is, because this was our first example, do we have to overwrite the instruction pointer? No, this is just one trick to get into a weird state. We could also use any other means to get into a weird state. Controlling the control flow in general can bring you in a weird state. If the attacker can control it, then it's easy, it's straightforward to get into a weird state just by calling this address or returning to this address. There are many ways to change instruction pointers. For instance, there might be things stored in memory like function pointers, vtables in C++ objects, different sorts of jump tables. You have the GDT, for instance, you have the PLT, all kinds of different tables and storage locations for pointers, for instruction pointers, function pointers. And controlling an instruction pointer even is not a requirement. Sometimes you can also control other data. You, for instance, can control the data that is used to decide whether one or another function is executed. So you don't have to manipulate the instruction pointer, but it's very convenient. Control flow hijacking, basically the part where you manipulate the instruction pointer in the end, is called control flow hijacking. So this is a category of tricks, and there are alternatives to control flow hijacking. But we have the mindset that we provide input, and this input programs our application in a way that was not intended. And we can program different parts. We don't have to change where in the code we jump. We don't have to change the control flow. We can also change the flow of data. For instance, modify the data used in a finite state machine used for the transition. So changing data to something that is not intended in the original finite state machine will also bring us into a weird state. For instance, assume the getAs bug gets fixed and we replace the function by fgetAs, right? fgetAs, much better. So we have the buffer here, 16 characters, fgetAs buffer 16, and we read it from standard in. This is a lot better, right? Something that we've ignored before is this debug mode. What is this debug mode for? Let's take a look at this. So this is actually an additional state in the finite state machine that echoes the input. So we look at the finite state machine again. We have the read pin, we have show pin, then check whether it's correct. If it's not correct, we print an error message. If it is correct, we show the password list. So the security properties basically stay the same, right? It should only provide a person or an attacker with the output if the person or attacker knows the correct pin. If the attacker doesn't know the pin, then we won't get the output. Let's compile this with W format security. All warnings enabled, W extra. And there's still a warning. Format not a string literal and no format arguments. Printf buffer. Have you seen this before? Printf buffer? This is fine programming wise. But we haven't seen a warning before. Why is this a format security warning? What is the problem here? So maybe let's check again the man page for printf. So the man page for printf says code such as printf foo often indicates a bug since foo may contain a percentage character. Oh no, please not. If foo comes from untrusted user input, it may contain %n, causing the printf call to write to memory and create a security hole. %n, does anyone know what %n does? Can someone in the chat maybe tell us what %n does? N sounds like a length. %n. Let's maybe think a bit more about printf. So printf can create a security hole, load a variable of a pointer. Why can printf write to memory? Maybe we should look at this in more detail. So it's supposed to print text to standard output, right? We never talked about printf as in reading something and then writing it to memory. It's about printing the contents from memory. But let's take a look at this. This is the printf we know. %d equals equals null x %x, and then we can say 20 and 20, and then we would print the number in decimal and in hex. These are format string parameters that we know, right? %d, %x, %s. We know these parameters. They are used to convert parameters, function parameters, into strings. But what if the number of format string parameters does not match the number of arguments? The function printf does not know how many arguments there are. So printf does not know that you haven't passed enough arguments. So this is already a problem, because if the user can provide a format string, the user can provide way more percentage identifiers, way more format string parameters than you have passed arguments here. As in our example before, we had printf user input. Then user input is a format string, and we have no parameters to the function, so the input if the input does not contain a format string parameter, it's fine. But if it does, then we have a big problem, because we will output a register value or a stack value or something like that. Let's take a look at that. Let's set debug to 1, and we enter the pin here. This is our pin, %x, 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 %x. Let's see what happens now. Oh, great. This looks like addresses from the stack, right? Values from the stack. Very nice. It was the wrong pin, of course, but now we have the values from the stack. So this is also a weird state. We print values from memory, and this printing values from memory is definitely not in our finite state machine. This is not intended to happen. So how can we program this weird state? And there we get to this format string parameter that is little known and that you might have overlooked so far, %n. The number of characters written so far is stored into the integer pointed to by the corresponding argument. This can be very helpful if you want to store how many characters you have printed. And then you just add %n and a pointer to an integer variable that you placed on your stack, for instance, and you can store how many characters were printed. That argument shall be an integer pointer or a variant whose size matches the optionally supplied integer length modifier. So for instance, let's take a look at this. Printf some string %n, and then count here, and then we can later on print. We wrote %d characters, and let's take a look at this example. This prints wrote 12 characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Perfect. Wrote 12 characters. But that means with %n, we can write values into memory, and it takes this address here and writes to this address. Interesting. So can we use that to manipulate data? Well, if there's an address on the stack, we can write to it without directly overwriting data from a buffer overflow. But this time we let the program in its weird state already modify its own instruction pointer. We are already in a weird state, and now we will enter another weird state. So the format string is on the stack. We can put any value there. So we can place any value onto the stack. Yeah, and this can be the address that we want to write to. Let's, for instance, place this address here, 1, 2, 3, 4, and then %x, 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 %x. Okay, let's run this. And if we run this, we can see that now our values are stored here on the stack. Very nice, very nice. Because the format string is stored on the stack. It's the buffer array. Okay, this is very nice. And now we can also extend this a bit. So maybe let's put a pointer here, a valid pointer. Okay, let's see. Oh, and this is now printing some weird characters here, but we can see our pointer ends up in the memory. Very nice. Now we have to exploit this. So we add our parameter %n instead of the last x. Now we do not read from this last offset, but we write to it. And let's see what happens if we write to it, because this is the offset for the return address again, and we can see that we overwrite the return address again, and we again print the passwords. With %n, we overwrote the correct variable at this address. Yeah, okay, sorry. Yeah, we overwrote the correct value, so it's not 0 or 1 anymore, but we instead overwrite it with n up there. And then, because this is the address of the correct variable, we have the value of, I don't know, what will it be, something like 9 or so, but 9 is definitely not 0. And that means that we now take the different branch at the if condition that decides whether or not we print the password list. So even without modifying the instruction pointer in this example, we still stay on the correct control flow. We still modify the program behavior in this data only attack. So we don't modify the instruction pointer in this example. So we just programmed the weird machine using user input, and we can transition to the same state, show password list again. There are many different memory safety violations. All of them get you into a weird state. or can get us into a weird state. They don't necessarily have to. Let me just okay, and let's continue. So far we have seen 2 of them, but there are of course a lot more. There's an endless amount of memory safety vulnerabilities that we can exploit, yeah, they are just a bag of tricks that we can select the right one from and can take any of these to get into a weird state. Our weird machine programs so far were quite simple, but in many cases they are more complex. So far we jumped to a sane state from the finite state machine, but we can instead also inject our own code and jump to that. And then we would jump into the middle of a sane state. It's another option. Or we can chain up multiple of these jumps. And with that, we get to this evolution of programming languages for weird machines. This started maybe with the Morris worm, that was the first internet worm, and the techniques over the years got more and more sophisticated and powerful, but also more clear. So the next part, maybe stack buffer overflows, also from the 90s, return to libc. Return to libc is very similar to what we have just seen, where we jump to a function that is already in the program, and this jumping to this function will then be exploited and, for instance, print us a secret variable from the program. Later on, this was more generalized into return to libc chaining, so multiple of these operations chained together. Then we had the borrowed code chunks, and this was then generalized into the techniques that we use a lot today, return-oriented programming, which can also be performed in very constrained situations where you can't even see where exactly you are in the address space for your exploit. So in this case, return-oriented programming is what I mentioned before briefly, the chaining together of many of such very short gadgets, and these gadgets would not be an entire function, but instead you would jump to an instruction that is close to the end of a function, and there the next return follows. So you place the next fake return address on the stack. So you would place your entire list of fake return addresses on the stack, and by that chain together arbitrary code execution. That sounds interesting. I want to learn more. Sure, there are many techniques and cool tricks, and if you haven't looked at them, it's more important for now to understand the concepts. The theory might be boring, but actually, if you look at them more specifically, this can help understanding the techniques. So if you really want to learn how these techniques work, participate in a CTF, try it out yourself. There's a CTF team at our university, the Los Fuzzies. They do this as a sport. They participate in competitions where they do this as a sport. And this is definitely something you can try. Just participate there, maybe once, maybe a few times if you like it. This will help you for understanding this topic, and it will also greatly increase your market value as a computer security expert. So we want to fix all the things, and fixing all the things, we are on a road of success there. We got rid of getS, we got rid of format string vulnerabilities, right? We have these warnings. So if we write secure code, we will fix these warnings and we don't have these bugs anymore. But maybe we couldn't find any other bugs. Then I would say the finite state machine emulator, which is our code, would look secure. But does that mean that the code is not exploitable? Can we maybe even prove that it's not exploitable? The question is, can we really do this? Not really, because we would have to check all weird states to check whether they are exploitable. How do we know which weird states are reachable. This is difficult. And this depends on the attacker model. What can the attacker do? So in a generic case, saying that the program code is not exploitable with respect to any attacker is very, very difficult. It is also difficult to think of all the attacker models. Many of them have not been discovered yet because we don't know the attacks yet. One example that you've already seen on the slides very briefly that I will also get back to is Rowhammer, where for a long time the attacker model was that an attacker cannot just modify the contents of arbitrary memory locations without having the permissions to do that. And with Rowhammer, this became possible. So this attacker model is now new, and you can't really foresee such events when new attacker models come up, and mitigating attacks of this type is quite difficult. Let's continue with the Menti. So I will, I want to ask you a simple question in the Menti, but before we do that, I will go through the Q&A. So let's check out the Q&A. Okay, things are about to get gruesome. That sounds gruesome. What's your opinion on Rust? Do you think it's a good, safe alternative to C++ and Co? Memory safe languages are not a new thing. We have had memory safe languages since many decades, and actually we moved from more memory safe languages to less memory safe languages. Before we used C++ and C, or around the same time they came up, but also before that, there were languages that were more memory safe than these, especially for C++. There were other languages around the same time and before that had better safety properties, but also C and C++. You can write completely memory safe code in C++ if you avoid certain types of operations. Do you want to do that? No, we probably don't want to do that. So does Rust give us an advantage here? I think like many programming languages, Rust will find its place. I'm not entirely sure how significant the market share will be. I'm more on the side, on a skeptical side for the market share of Rust. How much did you pay for the stream setup, microphone, etc.? I think around 1,000 euros in total. But I mean, if we use this over the next 15 years until the Corona crisis is solved, then it might have paid off in the end. Does the password manager example override pointers also work with activated ASLR? No, this example was without ASLR. It is still possible with ASLR, but things get much more complicated. And then usually you first need an information leak that tells you where things are. But for instance, if you would take the format string, we can use the format string to print the address of a local variable. So we already know where things are. So we can break the randomization by passing just the %x there to, or multiple of these, to print a function address or a local variable address. In this case, we are interested in local variable address. And then we will override this by providing a pointer that is shifted by the offset that we computed from this. No, I never am Biden or Trump. I guess many people in Europe were surprised that the US election is that close after the past 4 years. So I'm also surprised that it's that close. Can you teach us how to use Ghidra or Radare 2? probably not the best person to teach you how to use Jitra or Radare 2. You will learn to use them maybe in security aspects and software development in the masters. Also, if you want to learn how to use them, it might be a good idea to just participate in those CTFs, maybe in the Los Fuzzies team. Yeah, that's that would be a good opportunity to learn to use them. I haven't used them a lot myself because I'm moving more and more into a management and teaching role and less of an implementation and hacking role. Should have gotten a grant from the uni, yeah, but I mean, no one asked me to buy this streaming setup. Actually, we have a decent streaming setup at the institute, but I wanted to have something more specialized, more fit to my needs. How did we find the return address location again? The return address, if you think about the, let me just hide this for a second. If you think about the stack, we had the stack going from here to here, and we had the return address here, then the saved base pointer, the EBP or RBP from the old function, then the local variables from the old function. Then we call the new function, so we get again the return address, the base pointer, and the local variables. The local variables, so we place them downwards. Now a buffer grows from lower addresses upwards. So if the buffer is overwritten beyond its bound, it will overwrite first the base pointer and then a bit later the return address. So let me show the Q&A again. What was the weirdest? Does it work? What was the weirdest bug you've encountered by accident and thought that can't be secure? Oh, difficult question. Maybe the thing that I would consider the most remarkable bug that I've encountered more or less by accident. I mean, we were searching for it, but discovering things like that is always to some extent luck also. Was probably Meltdown, where I had conversations about this exact bug with different people more than a year earlier before we discovered it, and actually I think almost 2 years before that. And the thing is, I said that this is so unlikely that this bug exists, because people would have discovered it by accident already, because it's so obvious. So this is why it cannot exist, and this is why we shouldn't invest too much time on searching for it, because it will not work anyway, because otherwise people would have discovered it already. And by that, I deferred our search for Meltdown for almost 2 years. And yeah, we could have found that earlier. Wrong decision, but that's how it works. What is a CTF? A CTF, capture the flag competition. It's you could call it a hacking competition, but it sounds, if I would say a hacking competition, it sounds very it sounds like as if you have to be a hacker, but it's more like a sports event where it's easy to participate and learn. So it's also a learning environment. So you can go to our local Capture the Flag team, to the Los Fuzzies, and they will integrate you into their events. And if they participate in a sports event, in a Capture the Flag event, then you can participate. And even if you only find a single bug, or even if you only help in the discussion, only if you only are there for learning, this is already a big contribution. If you at some point find the bug, then this helps the team already. Of course, this is at first learning, but at some point, and this goes pretty quickly, you will discover bugs on your own, and then you will also on your own figure out how to exploit them. These capture the flag events usually also have different difficulty levels. So there are capture the flag events that are entirely in its entirety easier than other capture the flag events. But also within one capture the flag event, this usually consists of many different small challenges, and some of them are very easy. So you would probably after this lecture even be able to solve the easiest of these examples and on your own. And for the others, maybe you have to talk to someone else, maybe brainstorm a bit with someone else, and then you would also find the solution. And for the really complicated ones, you need a bit of more experience. But this comes while participating in these events a few times, you gain the experience there. Okay, with that we are through the Q&A for now. I will hide the Q&A for now, and I will go to the next question. Let me maybe check this one again. So okay, the majority is for 9:30 to 11:45 and including a 5-minute break. So most people want to have 15-minute break. Most people want to have a break. Today we don't make a break. We only have 40 minutes left, so we are already on the finish line. Let's continue with a word cloud. Oh, it didn't say what I want to have as a word cloud. So the question that I want to ask you here is, who is interested in exploitation? Which actor? Maybe you can tell me actors internationally, nationally, who could be interested in exploitation of bugs. I want to know which roles, which actors there are. Governments, CIA, NSA, sure. Hackers, nerds, banks. Banks interested in exploiting bugs. I'm not so sure, but maybe they are interested in the existence of bugs. Bug bounty hunters, companies, and that also relates to the bug bounty hunters, yeah. Pen testers, yes. I will just close the window. What else do we have? Me? Yeah, I might be interested in bugs, but also hopefully you, right? I hope you are interested in exploiting bugs. Researchers, security companies, hackers, governments, NSA. Yeah, NSA is the biggest one here for whatever reason, right? Okay. Very interesting. So let's see what I've put on my slide here. What I have on my slide is who is interested in exploitation: criminals, vendors, and governments. Yes. So why are they interested in bugs? Well, let's talk about what types of bugs we are talking about. Let's talk about the criminals. And let's start with the really, really evil criminals. The criminals that want to copy games, for instance, or gain privileged access on their own device. For instance, an iOS exploit, iOS 0 days. 0 days are exploits that are used in the wild, and they are called 0 day because when they are entirely new. It's an undisclosed vulnerability that is used in the wild. So at the point when you disclose them, or when the vendor knows them, then you don't call them, at some point you don't call them 0 day anymore, because the vendor had time to patch them. In the V, we had also buffer overflow in The Legend of Zelda Twilight Princess. This hack was then called the Twilight hack. The PlayStation 2, we had a buffer overflow in the BIOS. PlayStation 3, a heap overflow. Xbox, a buffer overflow in save games. And for these bugs, you can exploit these bugs for jailbreaks, and you can also earn money with that. And here we are at the ethics. The vendor has 0 days to fix it when he sees it. Yeah, you could say it like that, maybe. This is the payout ranges from Zerodium. Zerodium buys 0 days, and they will sell 0 days then to interested buyers who would like to buy a 0 day. Let's look at the numbers here. So we have here up to 1.5 million for an Apple OS, for an Apple iOS 0 day. 1.5 million. Who would pay 1.5 million dollars for a 0 day in an Apple iOS? Let's talk about 0 days in government. So what do governments need 0 days for? For computer and network surveillance. Sometimes governments use state-sponsored Trojan horses. For instance, in Germany, the Bundestrojaner, in Switzerland, the Mini-Panzer and Megapanzer, and also in Austria, there's the so-called Sicherheitspaket. And all of these techniques have the idea that they, for instance, can bypass end-to-end encryption because they intercept messages already before you encrypt these messages. And for that, you need to have some way to gain code execution on the device, permanent code execution ideally. In the NSA exploits, we also have seen many of these 0 days, actually a lot of 0 days, and they actually have later on been exploited by criminals as well, because it was not easy to fix all of these bugs in a short time. That much about people who are interested in bugs. Maybe criminals don't pay that much, but maybe also criminals pay a lot of money. Maybe let's stay here for a second before we go over to the defenses. Of course, you can make a lot of money by selling vulnerabilities to companies like Zerodium, or to even better on the black market on some black market platforms. You might even get higher prices, really high prices. So the question is, why not do that? This is a lot of money, good money, right? The question is always what happens if you do that. If you find a 0 day in iOS, you sell it to some black market actor or to a company like Zerodium, where will the 0 day be ending up? Will it be ending up in a maybe authoritarian regime that will use this exploit to spy on minorities, maybe to spy on people that are then later on imprisoned, or even worse, depending on the local legislation, have to face death penalties. This is very, very dangerous, and you always have to think about the ethics when dealing with 0 days, or in general with vulnerabilities. It's important, I think, and this is where also the 0 day activities around 0 days from governments are not really contributing to society, because these bugs are still out there in the wild. Criminals can exploit them. Just because the government paid money for that doesn't mean that the same bug is not also exploited by criminals. And now if criminals are using this, and the government paid a lot of money for that, let's say Austria paid multiple $1 million for a 0 day to spy on their citizen. Do they have an interest to get the bug fixed as quickly as possible? If the bug is fixed, then they can't use this anymore. They can't use this anymore to implement their Sicherheitspaket. So this would be wasted taxpayer money. So this is really, really difficult. And the governments, of course, don't have an interest in in throwing away the 0 days, so they won't just buy them and then get them fixed as quickly as possible. But these 0 days, they will survive over many weeks, months, even years. Yeah, pretty dangerous situation, because everyone can be attacked with these 0 days. Not just the government can use them. Let's talk about defense as something more positive. There are many people that are like, oh, attacks. I actually got a lot of these questions during my PhD. Actually, for my PhD defense, one of the questions was, why are you only working on attacks? And then usually this is followed by something, do you just want to see the entire world burn? And no. But someone has to find these bugs, right? For the blue team, right? They want to come up with defenses. And we came up also, my team came up with defenses as well. You will have all the KPTI patch in your Linux. You will have the, what is it called on Windows? KVMA or something like that, KVSA, something like that. It's the same principle, and this is all based on a patch that Michael Schwarz, Moritz Lipp, and I developed together with Richard Fellner, who was a master student in our group. And this patch was merged in the Linux kernel. It's now in every Linux kernel. The same principle is implemented now in every operating system out there that you use on modern computers. The patch from a master student, from TU Graz, from our team. That's quite crazy. And if I say the team from the patch from our team, actually Richard did most of the work, to be honest. The master student did most of the work, but in the corner cases where it got tricky, we helped out here and there. So defenses in computer science or in computer security is surprisingly hard. Defending against attacks is really hard. In the classical war games, there's the 3-to-1 rule. An attacker needs 3 times as many soldiers as the defender. But in computer security, this is not the case. In computer security, you have the disadvantage on the defender side. In general, this is a rule of thumb. In computer science or in computer security, the defender has the disadvantage. The attacker just needs to find one vulnerability, and this vulnerability then can be exploited on all the products out there, on all the devices out there. I think it's just, I don't know what this comment is referring to, but if you clarify, I'm sure that I can clarify. The disadvantage for the defender is that the defender has to protect against all possible attacks, and this is a problem of security. You will also see that measuring security is immensely difficult. Think about something like safety, car safety. You can measure safety, and we have learned how to do that in the past 100 years. We learned that safety belts, for instance, increase the chances of surviving an accident that would otherwise be fatal. Right? If we drive into a concrete wall with a car with 50 kilometers per hour, if you would have done that with a car, let's say 60 years ago, you would have been certainly dead. If you do that today, actually the cars got quite good at protecting drivers. So in many situations, you will survive accidents like that. And you can see that the statistics of how many people die in traffic accidents, in cars, in traffic accidents, has been going down relative to the number of drivers over the past few decades, since we started realizing that going as fast as possible is nice, but also not dying is also nice. Yeah, it's something nice to have. But in security, it's difficult, because how do you measure it in security? How do you measure how secure you are. You cannot really measure. You cannot really say I'm 7 secure. What does it mean, 7 secure? 8. I'm 8 secure. I don't know. 15, 100 secure. There's no meaning to say I'm that much secure. You can say I'm protecting against these 500 attacks. But what if you don't protect against these 500 other attacks that give the attacker the exact same capability? What does security then even mean? So security is immensely difficult to measure and quantify. So the problem here is that the defender has to protect against all attacks, because all of these attacks that are not mitigated could provide the attacker with the same capabilities as the one vulnerability that the attacker already has. If the defender misses one vulnerability, the attacker wins. And then, the best defense is good offense. No, that doesn't work here either. What do we do in computer security? Mainly there are 2 strategies. Strategy 1 is you have a company that has a red team and a blue team. The red team finds all the bugs and the blue team fixes them. And this continues forever. They will never stop searching for bugs, and the blue team will never stop fixing bugs. Strategy 2, find more generic mechanisms such that the red team cannot exploit the program. Often strategy 1 is used that seems simple and cheap. It's actually not necessarily simple and cheap, because you have to run this constantly. It took an attacker researcher more than n months to find a bug, so the cost of finding the next bug is greater equal to n months. Could we say that? Would that be a statement that makes sense? No. This guy would say this is wrong. This is all fake. It's not how it works. So how does it work? Let's recap weird machines. We defined exploitation as a 3-step procedure: setup, instantiation, and programming. And the fix prevents one weird machine or programming of this weird machine. If you have similar bugs, then you have similar weird machines. And if you want to fix all of these bugs, you will have to fix all of these weird machines or the programming of these weird machines. So by doing this strategy 1, by running this strategy 1, it will constantly require resources to fix all of these bugs. There's the question then, what is the cost of finding bugs? So let's think about the cost of finding bugs. If you search for bugs, with the number of bugs, the cost basically goes up. Every bug, you need to invest a bit of cost, and then you will have the same amount of cost for every bug maybe. But in reality, if you think about complex bugs that are difficult to exploit, it goes up. And then, you still might be able to constantly find these complex bugs. But for simple bugs, you will initially find some. The cost then stays very low for a long time, because you can find all the similar bugs, right? In the beginning, you have to invest some, and then it stays almost at no cost at all, because you can automate this part. You can write scripts that search for these types, these classes of bugs. But at some point, you will have found all of the bugs in this class, or your way of finding bugs will exhaust the state of the program. So maybe there are further bugs in this category, but your approach to finding them might not find any further. So then the cost of finding further bugs increases again. So finding simple bugs, easy to exploit bugs, might get more expensive then later on. Simple bugs become more scarce. Complex bugs that involve the interaction of many different parts of the program, they stay the same for a longer time. Strategy 2 would be the academic way. Basically think about what would be the more general thing that we can do, the more general protection. As you will see it also in companies, they are now more and more adapting to this. They call it defense in depth. defending against entire classes of bugs, even if you only know of a single bug, or preventing the exploitation of entire classes of bugs, even if you only know one specific instance, or even before you know a specific instance of a bug. For instance, the Kaiser patch was designed for one bug and then deployed against another that we didn't even know. We didn't know Meltdown at the time that we developed the Kaiser patch, and now it's deployed against the Meltdown bug. So we want to design defenses that kill entire classes of bugs, for instance, buffer overflows. But this can be extremely hard. It's not easy to find or develop bug-free programs. But if we prevent exploitation, we have already won. So what we want to do is we want to prevent one of the steps of the exploitation. For instance, the setup step, but the setup step is actually just a regular insane execution of the program. Maybe the instantiation step or the programming step. Yes, for these we have transitions into weird states or from weird states. Maybe there we can implement mitigations. Let's start with the instantiation. And we again start with our simple password manager as an example. We have our state machine here, we have our program here, and we want to solve this bug. So let's assume that the red team did not find any bugs in here, not yet. And we don't know about the getS and printf bug. So let's assume we don't know about any of these. The blue team now has to defend against attacks that it doesn't know yet. So it will make assumptions about what could be attacked, what would roughly be a possible attack. Yeah, protecting against an unknown attack is often not possible without, for instance, a great performance overhead, because you often have to mitigate way more, prevent way more attacks than you anticipate that you actually want to prevent. For instance, the Kaiser patch prevents way more than just the Meltdown bug, but also it comes with a significant performance overhead. Now, let's assume that we know about stack buffer overflows. Could we prevent stack buffer overflows? We want to prevent the instantiation, so the attacker should not go into a weird state using a buffer overflow. So the program should rather die than being attacker controlled. That's the idea. Okay, maybe we have to think about how that works. The stack overflow overrides the saved return address, right? We had this array, we override the return address. Maybe we can prevent that. Can we make the stack read-only? No, that doesn't work. The stack has to be writable. But we might have a different idea. And this idea, you might know this actually from coal mines and other mines. There, this technique has already been used. It's a simple idea. You put a known random value between the buffer and the saved return address. And in the chat, someone already called it, yes, a canary. We call this value a canary. The canary is overwritten first because it's placed between the buffer and the instruction address. On return, before you use the return address, you check whether the canary is still alive, or whether it still has the correct value. If not, you have a buffer overflow detected and you kill the program. Let's try whether this works. So we have our program here, we have our stack here, so we have the instruction pointer, the base pointer, the canary, which is a random number in this case. We have our buffer. We overwrite the buffer, so we go beyond the buffer. We overflow the buffer into the canary, into the base pointer, into the instruction pointer, and the return will now check, is the canary the same? It's not, so we exit. So stack canaries are great, and stack canaries are by default in GCC today. However, only buffers larger than 8 bytes are protected. So very small buffers are not protected. Unless we pass special compilation flags, then we can also protect our very small buffer here. So we can see here, maybe, yeah. It's always weird if the head goes missing. So we can see here that stack smashing was detected, and this cannot be exploited then because the application crashes instead. So we fixed the class of bugs, we fixed this entire problem. The canary protects every stack buffer from being used to get into a weird state. Perfect. Wait, this is again wrong? Oh wait a second. So what is wrong here? So simple stack buffer overflows cannot get into an exploitable state anymore. Okay, but what if we leak the canary using a different trick? For instance, the printf bug that we have seen before. We can print the canary using %x, providing a format string, or using an out-of-bounds read. We can read the canary. So this only prevents a part of this class of bugs. There are still other ways to get into the weird state. We want something more generic, but something more generic, even if it's less powerful, but something that really prevents a class of bugs. Any alternatives? Maybe we can prevent something else, not the instantiation step. So in the second step, we overrode the saved instruction pointer on the stack, so we got into the weird state. Maybe we can separate the saved return address and the buffers on the stack. We can have separate stacks. And this is also a simple idea. We have two different stacks, one safe stack and one unsafe stack. And the safe stack is used for return addresses and simple variables maybe. And for buffers, we use the unsafe stack. This can overflow as much as it likes. Buffer overflows cannot override the return address anymore. And then it would look like this. We have the normal stack here. We have a safe stack here, unsafe stack here. And you can see this is split up. The normal part is split up into two parts. And if we call a function, we have the return address here, the base pointer here, and we place our buffer here. If this overflows, it will only override other local variables. Perfect. CLang supports a safe stack with a compile flag, which is very nice. You just provide this flag, fsanitize safe stack, and then you have a safe stack. Perfect. Let's try what this does. So we provide 1, 2, 3. Okay. Let's try a longer number and it didn't. This didn't crash. Interesting. So we overrode maybe a different buffer, but certainly not the instruction pointer. That sounds good so far. But until now, we only prevented very small classes of bugs. It looks like a cat and mouse game because someone will find a different way to exploit this, and then we will need more defenses. So maybe we can do something else, something that prevents things in a more generic way, because adding more and more countermeasures costs a lot of performance, memory, but also money for developing all these countermeasures. We want something more generic, and we will take a look at something more generic. Maybe randomness. Someone in the chat already mentioned randomness. This is often used in security, so maybe we can use a probabilistic approach. The assumption is that the attacker can jump to any memory location, but what if all memory locations are unpredictable? And I'm not talking about unpredictable with cryptographic guarantees, but unpredictable enough that it's not feasible for an attacker anymore to try to exploit this. So the attacker cannot reliably jump to a specific location anymore, and this technique is called ASLR. Let's take a look at this address space layout. You might know this from operating systems, or from system level programming maybe. You have code, data, BSS, heap, shared memory, shared libraries, stack, and maybe they are placed somewhere else in the address space, but you will have a memory layout that is similar to this. Now, if you have ASLR, what happens? They will be mixed around. They will be moved. The offsets will be moved, and you will not be able to predict where things are. The attacker cannot predict it, and then the attacker cannot inject the right address. This is very powerful on 64-bit systems because they have a huge address space for the user space, which is 128 terabytes. 128 terabytes. Wait a second, 2 to the 64 is not 128 terabytes, right? Maybe you remember that this doesn't fit together, and what the reason for this was? It's 48 or 47 bits of virtual address space actually for the user space, 47 bits. ASLR is only a probabilistic countermeasure, but it has a really, really big advantage. If you keep the addresses secret, then things are fine. If you leak addresses, of course, it breaks immediately, but it has a big advantage, namely that it makes exploitation hard, in some cases really hard, and the cost is almost nothing because we have to place the data in memory anyway somewhere, and why not place it at a random offset? This offset computation doesn't cost anything, so it is very, very widely in use. If the randomization range is large enough, then things are fine, and this is why it's used very widely, almost no cost, even if it only brings probabilistic security. Yes, ASLR is very widely used. Linux since 2005, since 2014 in the kernel, Windows since 2005, Android and iOS since 2011, macOS since 2011, since 2012 in the kernel. So this is very popular. This prevented many, many single bug exploits as they fail with a high probability. So in the worst case, they make a bug more expensive because you need, in worst case from defender's perspective, they make a bug more expensive because you additionally now need an information leak. In better cases, they make a bug exploitation unreliable, and in the best case, they prevent bug exploitation because the attacker cannot retry the exploitation as often as it would be necessary to actually exploit the bug. So the next step then is preventing the programming step. Here the assumption is that we can still, let me just think about, because I'm seeing the time now, and I'm wondering whether we should maybe continue here in the next lecture. Let me check. Yeah, probably I will continue here in the next lecture. So we will not continue with the programming step now, but instead we will go to the Q&A and do the programming step, preventing the programming step, in the next hour, next week. Let's go to the Q&A. There are a lot of questions and I would like to answer them first. Did you get weird job offers after Meltdown? I did get many different job offers around the time after Meltdown, because this was also shortly after I finished my PhD, and so this was the time where a lot of people want to hire you. What do you think Meltdown and Zombie? What do you think Meltdown and Zombie Load would be worth if someone would have found and sold it? For Zombie Load is a bit trickier to exploit than Meltdown. Maybe Meltdown was so blatantly, stupidly easy to exploit. I think this would have been very, very much money. This would have been a tremendous amount of money if you would have found this and sold this on a black market, because this affected every computer and it allowed to leak basically any data on any computer, regardless of it. Even worked across operating systems. So this is a really, really good case. On the other hand, Meltdown only gives you access to all the data on the system. It doesn't give you something like persistent code execution. So it will be very valuable in terms of information leakage. and there it's certainly very significant. Especially because you can also leak cryptographic keys, SSH keys, for instance, and then use these keys to work on further exploitation. Maybe also leak password hashes that you have there, leak any confidential information on the system. So this is definitely an attack vector to consider. But for many exploitation types of exploitation, especially if you talk about criminals, they are often less interested in leaking information. They are often more interested in obtaining persistence on the system with code execution. Okay, North Korea, I think that's a comment, I'm not sure. NASA, try hacking a rocket. Not sure what the comment means. What were the biggest players that tried to hire you? So in many cases, the hiring runs under mutual agreement of non-disclosure. So I will not disclose these things. What is LVI? LVI stands for load value injection, and it basically turns the meltdown attack around. With the meltdown attack, we will also talk about this in the lecture, we can leak data values from other processes on the system or from the kernel, and with LVI we inject wrong values into another process that then operates on these wrong values. That is why it's called injection, and we inject these wrong values into load operations, therefore load value injection. With that, we are already at the end of the Q&A. I still have 3 more minutes according to the schedule, so if you have any further questions, feel free to ask them, but I have to leave on time, and I guess it would also be fair for, to you to finish on time. Now I switched to the wrong color of the light here. Okay. Well, if there are no more questions, I would say if you like, you can give me another round of applause, and let's. There is another question. Yeah, we still have time for the question. Will we be the attacker or defender at the assignments? I haven't checked out the assignments from this semester, but I would expect that you will work both on attacker tasks and defender tasks, maybe very simple ones. But I could be wrong, but I would definitely assume attacker tasks. Okay, thanks for your attention, and if you like, you can give me another round of applause, and I will hide this here. And thank you for your attention.